Hello, I'm Sebastian. Welcome to 9R Trees podcast. Today, I will summarize and review the book. Relativity for Beginners by John Stoddard is a plain English guide to Einstein's special and general relativity, written for readers who want the big ideas without heavy mathematics. The book frames relativity through a small set of core discoveries that reshaped physics and everyday intuition, the way motion changes measurements of time and distance, the role of the speed of light as a universal limit, and the deeper insight that gravity is not a conventional force but an effect of curved space-time. Instead of assuming a technical background, it aims to build understanding step by step using accessible explanations and practical mental models. Readers are guided from the basic question of how observers in different states of motion can disagree about measurements, into the consequences of that disagreement for simultaneity, energy, and gravity. The overall promise is speed and clarity, learning the conceptual foundation that makes later study, whether in popular science or more formal textbooks, feel less mysterious and more coherent. I will give you key takeaways from this book. Firstly, why the speed of light changes everything. A central starting point in beginner relativity is the idea that the speed of light in vacuum is the same for all inertial observers, regardless of how the source or the observer is moving. This is not just a curious fact about light, it forces a rewrite of what time and space mean. If everyone measures the same light speed, then ordinary ways of adding velocities cannot be universally correct. The book's beginner focus typically uses simple thought experiments to show the problem. Imagine timing a flash of light across a moving vehicle versus across a stationary room. If the light speed cannot change, then the only quantities that can adjust are the measured time interval and the measured distance. From this single constraint, many famous results follow in a logically connected way. Readers learn why relativity is not about optical illusion, but about consistent measurement rules. This topic also clarifies what is meant by an inertial frame, why experiments like interferometer measurements historically mattered, and how the postulate leads to new transformation rules between observers. By grounding the story in a small number of assumptions, the concept becomes less like a paradox and more like an inevitable consequence of demanding universal physical laws. Secondly, time dilation and the relativity of simultaneity. Once the light speed is fixed for all inertial observers, time can no longer be absolute. A major beginner milestone is understanding time dilation. Moving clocks tick more slowly relative to a stationary observer. The book's step-by-step approach commonly builds this from a light clock model, where a beam bounces between mirrors. If the clock moves sideways, the light travels a longer diagonal path, and because the speed of light is unchanged, the tick must take longer. Importantly, the effect is symmetric between inertial observers, which pushes readers to confront a deeper idea: simultaneity depends on the observer. Two events that look simultaneous in one frame may not be simultaneous in another frame moving relative to the first. This topic helps explain why relativity can feel bizarre at first, yet remains logically consistent. It also sets the stage for understanding classic puzzles such as the twin scenario, where acceleration and frame changes break the symmetry. By focusing on concepts before formulas, the reader can internalize what time dilation means operationally, how you would measure it, what counts as a clock, and why the result does not contradict everyday experience at low speeds. Thirdly, length contraction, spacetime, and invariance. Relativity does not only alter time, it also alters measured distances along the direction of motion. Length contraction says that an object moving relative to an observer is measured to be shorter in the direction of travel. Paired with time dilation, this completes a consistent picture. Different observers slice space-time into space and time in different ways. A beginner-friendly treatment often introduces space-time diagrams, or at least the idea that events are points in a four-dimensional arena. The key payoff is that while observers disagree about separate amounts of time and distance, they can agree on certain combined quantities. This is where the concept of an invariant becomes powerful. The laws of physics take a form that is the same in all inertial frames. Even without deep math, readers can learn why invariance is the real goal, and why the old notion of absolute space and absolute time fails. This topic also naturally connects to limits and causality. Because light speed is a boundary, spacetime has a structure that prevents cause and effect from being reversed when information cannot travel faster than light. By presenting contraction not as a trick but as part of a unified geometry, the book helps the reader replace intuition based on everyday speeds with a new, more reliable framework. Fourthly, from special to general relativity, the equivalence principle. General relativity begins where special relativity begins, where special relativity leaves off. Special relativity handles inertial motion, but gravity involves acceleration and curved trajectories. The conceptual bridge is the equivalence principle, the claim that locally the effects of gravity and acceleration are indistinguishable. A beginner-oriented explanation typically uses the elevator scenario. In a closed cabin, you cannot tell whether you are in a gravitational field or being accelerated in deep space, at least over small regions. This idea reframes gravity as something that can be transformed away locally, suggesting it is not a conventional force in the Newtonian sense. The equivalence principle also predicts measurable outcomes. Light should bend in a gravitational field. Clocks at different heights should tick at different rates, and free fall should represent a kind of natural motion rather than forced motion. By emphasizing local experiments and operational meaning, the book can help readers see why general relativity is not just a stronger version of Newton's law, but a different kind of explanation. This topic also clarifies why gravity affects time directly, making gravitational time dilation not an add-on, but a central feature. The step-by-step narrative is designed to make this leap feel motivated rather than magical. Lastly, curved spacetime, gravity, and real-world tests. The headline insight of general relativity is that mass and energy influence the geometry of spacetime, and that geometry guides the motion of matter and light. In plain English, gravity becomes the name we give to the way objects follow the straightest possible paths, called geodesics, in a curved spacetime. Beginner explanations often lean on analogies like a stretched surface with a depression, while also warning that the analogy is limited because spacetime curvature is not just spatial. The practical value of this topic is that it links the abstract concept of curvature to concrete phenomena, the precession of planetary orbits, the deflection of starlight by the sun, gravitational lensing, and the shifting of clock rates that must be accounted for in technologies such as GPS. It also opens a window onto modern discoveries such as black holes and gravitational waves, which are natural consequences of the theory's geometric view of gravity. By presenting evidence and applications, the book helps readers trust the framework and see why relativity matters beyond thought experiments. The goal is not to turn the reader into a mathematician of tensors, but to make the conceptual predictions feel coherent, testable, and relevant to the way the universe works. In conclusion, this book is best suited for curious beginners, high school or early college learners, and adults who have heard about time dilation, curved spacetime, or black holes, but want a clean conceptual path that does not require advanced math. It can benefit a reader's life by strengthening scientific reasoning. You practice separating intuition from measurement, following a small set of assumptions to their consequences, and recognizing how good theories are built around invariance and testable predictions. That mindset transfers beyond physics into clearer thinking about complex systems. Compared with many relativity introductions that either drown the reader in equations or stay too poetic to be useful, this book aims for a middle lane, plain language, step-by-step structure, and a focused set of core discoveries that organize the subject. The value proposition is speed and cohesion. By learning how special relativity motivates general relativity and why both are grounded in experiments and real-world technologies, readers get a framework that makes later reading, documentaries, or more technical study dramatically easier. If you want an approachable entry point that still respects the logic of the theories, it is a worthwhile purchase. If you would like to support John Stoddard, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.